Now let's take a look at representing signed numbers. So if you recall, an unsigned number was one that represented codes that went from 0 decimal up to some number, which was represented as 2 to the n minus 1 as the highest value. And unsigned meant that you didn't need the sign number, or the sign. Now with a signed number, what it's referring to are numbers that have the sign in them. So for example, -2, -7 decimal. Notice that this is the sign. Now it was implied over here on an unsigned number that you had, this was actually positive 2 to the n minus 1, but we drop the positive sign when we're not really using it, so when we don't have negative numbers. But the sign is the negative sign, so that's where signed numbers comes from. So negative sign. Okay, so now what we're going to do is take a look at how you can represent signed numbers. And the most popular way to do that is to use the most significant bit in order to represent the sign. So let's take a look at how we do that. What we're going to do is we're going to say the most significant bit of a number, let's just take a 4-bit number, 0 and then whatever, is this is going to be the sign bit. And the way that this works is a 0 in this position means that it is a positive number. If you have a 1 in that position, you are going to have a negative number. Now, that's the general logic behind a signed number, and this is universal. So if you have somebody that says, I have a signed number, you look at the most significant bit and you say, that's the signed bit. As soon as you start talking about signed numbers, you need to fix the number of bits. So you don't allow the bits to scale arbitrarily. For example, if you had 1 1 and then you had 1 1 1 1, these can't be in the same system where you said, okay, the sign bit was the most significant bit, and then over here I kept adding to it and all of a sudden it moved over to here. That doesn't work. The way that you would say this is you would say, I have a 4-bit signed number, and then if you were given the number 1 1, that would imply that you had leading zeros up there, and the sign bit is that. So when you say you have a fixed width, you state the number of bits in your code, and then the most significant position, so for a 4-bit you'd be in position 3, that is going to be the sign bit. Okay, let's look at 3 common ways to encode numbers using, or encode negative numbers. Now the first 2 we're going to look at are called signed magnitude and one's complement, and these aren't really used much anymore. These were defined originally when digital computers started coming out, and they've had uses in real systems, but today what we use is the 3rd technique that we'll look at, which is called 2's complement. So we look at signed magnitude just to really motivate why we use 2's complement today, because without looking at it you wouldn't maybe know why we have chosen to use 2's complement in all of our computers. But let's take a look at it. So in signed magnitude, here's what you do. All you do is you simply use the most significant bit. So let's say I had 0 1 1 1, and this is going to be a 4-bit signed magnitude number. You use the most significant bit as the sign, and then the other bits are the absolute value of the number. Okay? So all you do is you simply take whatever decimal number you want, convert it to binary, and then plunk it into there. So let's take a look at an example. Let's say I wanted to encode -2, for example. So -2 in decimal, and I'm going to do it in a 4-bit number. What I would do is I'd say, okay, I'm going to find the binary code for 2, which is simply 0 1 0, and notice that I only use 3 bits because if I have a 4-bit number, I'm reserving the sign bit for something else. So I take that and then I append the sign bit. So then what I do is I put the sign out there. So this is how I would represent -2. Notice that this component right here is just the absolute value of 2, and if I wanted to look at how I would do +2, well, I simply use 0 1 0 again, and I just append a sign bit of a 0. So this right here would be +2. Notice that the absolute value, that's where the signed magnitude comes from, so the magnitude of the number is represented in n-1 bits. So you have n-1 bits for the magnitude. All right. So let's take a look at how we could create a table of signed magnitude numbers, and let's stick with the 4-bit example. So I'm going to come along and I'm going to take a look at this table right here, and notice that the code 0 right here, we have 0, 0, 0, 0, and let's count up. So for code 1, decimal 1, we're going to have 1, and then 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, and then we continue 1, 0, 1, 1, 1, 0, 1, 1, 1. Notice the sign bit is always a 0, and then we just simply, it's basically mirrored across this axis where you'll have -1 is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, or 1, 0, 1, 1, 1, 0, 1, 1, 1. So notice that going this way, we simply use the absolute value. All we did for these negative numbers is we put a sign bit in front of it. The drawback of signed magnitude immediately becomes apparent because you have two codes for 0. You're going to have a positive 0 and a negative 0. Now this is an issue because having two codes for 0, so this is an issue, two codes for 0 makes it a problem because you have a gap in your number system. And that means that if you were, when you're doing math, if you said I'm going to do -5 plus 2, the answer should be -3, and that would probably work. But what if I did -5 plus 7? So then that would be +2. The problem is that when you added 7 to -5, since you had a double gap for 0, this arithmetic wouldn't work using a traditional binary adder. So the two codes for 0 does not work very well. However, the advantage of signed magnitude is that it's very simple. It's a very simple encoding technique. You can look at it and everything makes a lot of sense. Okay, when we talk about signed magnitude or any signed number system, we want to talk about the range of numbers that can be represented. So if you think about the range of a signed magnitude, I'll put it as the numbers that signed magnitude can take on, it's going to go from -2 to the n minus 1 minus 1, and then up to positive 2 to the n minus 1 minus 1. Now why is that the range? If you think about it, we go negative and positive, so we split our codes equally amongst the positive and negative. That's why we did 2 to the n minus 1. So for the example that we had where we said, okay, let's take a look at n equals 3, which is this example. I'm going to say n is equal to 3, or excuse me, n is equal to 4. So I have 2 to the n unique codes, or 2 to the 4, which is going to be 16 unique codes. And then what I do is I split half of them for negative and half of them for positive. So I have 8 for negative and then 8 for positive. And they're symmetric about the 0 axis. Okay? So they're symmetric amongst the positive and the negative. Now, when I plug that in, if I came down here and I wanted to plug that in for my range, what I'd have is I'd have negative 2 to the 4 minus 1, which is 3, minus 1. So that would be less than or equal to n of signed magnitude. Then that would go up to positive 2 to the 4 minus 1, which is 3, and then minus 1. So if you looked at that, you would have negative 8 minus 1, negative 7, and then you'd have 8 minus 1, which is 7, so you'd have positive 7. So if you look at the range here, the range goes from negative 7 up to positive 7. So we were able to get a range of values. Now, what's the problem with that? The problem is that we didn't use all of our unique codes in our system because we didn't use all of our unique codes to represent a number. What we ended up doing is we used 2 of our codes to represent 0. So this not only was inefficient from an encoding standpoint, but it also created some issues when we looked at performing like traditional arithmetic because that gap messes everything up. Okay, so now what we want to do is let's look at the second common encoding technique for signed numbers, and it is called ones complement. So let's take a look at that. Now, ones complement is when you do an operation, which is actually called ones complement, on a number to find its negative. So this is going to be called 1's complement. Notice when you say complement, it's an E there. It's complement. Okay. So what is a 1's complement operation? The operation, very simple, is you invert or complement every bit. So you invert or complement each bit. And that means you're basically going to take a 1, go to a 0 to a 1, and a 1 go to a 0. So if I had a number like 111 and I took the 1's complement of it, it would go to 0, 0, 0. So all you do to simply find the negative number is you perform a 1's complement. So let's take a look at how we would do that. I'm going to make a table. Let's do an example where we have n is equal to 4 again. And I'm going to say for code 0, I'll have my decimal value here. I'll go code 0. So decimal is here. I have 0 as my sign bit, and I'm going to go 0, 0, 0. Now, I want to count up, so, excuse me, that'll be my decimal, and then this will be my code right here. So then when I go to 1, I go 0, 0, 0, 1. When I go to 2, I go 0, 0, 1, 0. 3, I go 0, 0, 1, 1. If I want to find the negative of that, so I'm going to put the axis right there, and I want to find the negative of that, I would simply complement everything. So in this situation, I'd have 1, 1, 1, 1. That would be the equivalent of negative 0, which again, you see the issue here is that you have duplicate codes for 0. And then we also have, for negative 1, what I'd do is I would just take this, and I would complement. So I'd have 1, 1, 1, 0. For negative 2, I would simply take 1's comp of that, so I go 1, 1, 0, 1. Notice that this works very well in terms of remaining or leaving the sign bit in the most significant bit. So all the positive numbers here correspond to a sign bit of 0. All the negative numbers have a sign bit of 1. And it's a very simple way to do it. And if I continued counting up, I would get to 7 is 0, 1, 1, 1. And then negative 7 would be simply, I would then complement that, and I would get 1, 0, 0, 0. So a couple things that are, good and bad about 1's complement. The first thing is it's very simple to find the negative number. You just flip all the bits. So it's a very simple way to go back and forth between positive and negative. There's still a drawback that you have duplicate codes for 0. So that means we're not using all of the unique codes to represent all the possible information we have. There is one advantage of this which helps and it motivates further the use of 2's complement, and that is that you have this idea of rolling over. So when I get to 0, 1, 1, 1 and I added 1 to it, I would have simply gone to 1, 0, 0, 0. Well, notice that that's actually the most negative code. So when I increment past the most positive code, I go back and I start counting at the most negative code. And that becomes very handy for counter circuits, as you'll see later. So that rollover impact, the rollover attribute of 1's complement is kind of a nice thing. Now, if you want to talk about the range of a 1's comp, what we do is we'll put n of 1's comp, and so we'll go 1's comp. It goes down to, again, negative 2 to the n minus 1 up to positive 2 to the n minus 1. So down to, negative, or 2 to the n minus 1 minus 1, and then positive 2 to the n minus 1 minus 1. Again, the negative 1 in the exponent is due to the fact that of this possible example, let's say we had 4 bits, we use half of the codes to represent our negative numbers, and we use half the codes to represent our positive numbers, so that's where taking 1 away from the exponent is. So in this situation where n is equal to 4, I would have negative, again, 2 to the 4 minus 1, and then minus 1. So that's why you would have 8 minus 1 codes over here, and then that would simply go up to positive 2 to the 4 minus 1 minus 1, so you'd have positive 8 minus 1. So that comes out to be negative 7 up to positive 7. The negative 1 down here represents the fact that it represents the fact that you had a symmetric case around 0 and you didn't use all of your codes efficiently. So if you think about that, We didn't use all of our codes because we had duplicate codes for 0, so we were symmetric around the 0, and we were able to represent essentially 15 unique values, so 7 negatives, 7 positives, and then 2 codes for 0. So we had 15 pieces of information for 16 unique codes. Okay, so that's one's complement. That then motivates our final signed number system, and this is what's used in all computers today, and that is 2's complement. So in a 2's complement system, we are trying to do 2 things. So we want 2 things that we want to address. Number 1 is we want to get rid of that duplicate code for 0, but we also want to preserve that rollover impact. So we want it to roll over. So the first thing that you got to do with the 2's complement is you got to do the operation. So the operation is very simple in binary. What you do is there's 2 steps. Step 1 is you take the 1's comp of a number, and then part 2 is you add 1 to it. So that's how you find the opposite polarity of a number. So if you have a positive number and you want to go to a negative number, you take the 2's complement of the code, and it also works going the other way. So for example, let's just say I had the code 0001. So this is positive 1 in decimal, and I said I'm using a 4-bit 2's complement code. And I want to find negative 1 in decimal. So what I do is I do 2 steps. I take the 2's complement, they call it also taking the 2's complement, or 2's complement negation. So negation. So what I do is I take 1's comp of it, so I flip each bit, and then step 2 is I add 1 to it. And so then what I end up having here is 1 with no carry, 1, 1, 1. So this code right here is equal to negative 1. And that's how you do it. So if you wrote out everything, so let's do our table again where you go decimal, and then we're going to have binary over here, and this will be 2's complement. Let's start with a 4-bit example. So we're going to have decimal 0, and that'll be 0, 0, 0, 0. And then we have positive 1, which we said was 0, 0, 0, 0, 0, 0, 1. And then if you said what is negative 1, well, it turns out that that code is equal to 1, 1, 1, 1. So that's negative 1. Now notice this is this is the first time we've had something that looks like this. So the negative 1 code is at 1, 1, 1, 1. You still have the sign bit preserved, but then you move to 0, 0, 0. So that's kind of interesting. We'll look at that in a second. So if I had 0, 0, 1, 0, and I wanted to find negative 2, what I would do is I would come over here, and I'm going to take the 1's complement of it, 1, 1, 0, 1, and I'm going to add 1 to it. So I'd get 1 plus 1 is 0 with a carry, and then 1 plus 0 is 1, no carry, 1, 1. So that now is negative 2. So I'd come over here and I'd go 1, 1, 1, 0. And you recognize that, number 1, you don't have any duplicate codes for 0. So by having this new encoding approach, you don't have the duplicate code thing. And it's kind of nice because if you extended this out, if we continued this exercise, we'd end up getting to 0, 1, 1, 1, and then if you wanted to find the most negative code for 7, let's just do that one last time just so we get practice with it. So I'm going to invert all the bits, 1, 0, 0, 0, and I'm going to add 1 to it. So what I'm going to do here is I'm going to have plus 1, I'm going to have 1, 0, 0, 1. So negative 7, I have 1, 0, 0, 1. And if you actually look at this, there's actually an extra code available. So since we've kind of we don't have a duplicate code for 0, we actually get to go down all the way to 1, 0, 0, 0. So we can encode down to negative 8. So this becomes a very interesting thing because we don't have duplicate codes, so we're able to have 16 unique codes representing 16 pieces of information. So this is the power of 2's complement. Another thing that's interesting about this is notice that each of these values, if I look at this table, so let's look at a complete table that's a little cleaner. If I look at this table, what I'm going to have here is I've got each of these, as I go through this increment from negative 8 up to positive 7, I actually am only one more. So if I added 1 to negative 8, I get to negative 7, and that's what the code looks like. Then I add 1, then I add 1, then I add 1, and I add 1, I get up to 1, 1, 1, 1, which is negative 1. I add 1 to it, and I roll to 0, 0, 0, 0. That still is acceptable. Every one of these codes is exactly one more than its preceding code. And when I get to 0, 1, 1, 1, I add 1, and it rolls over. This allows arithmetic to work because all the numbers are continuous. They're in a continuous sequence that increment by 1. So that's 2's complement. And if you think about the range of 2's complement, if we look at the final thing we're interested in, which is the range, what we want to know is what are the numbers that can be represented with 2's comp. Now what we have is we have negative 2 to the n minus 1, but we don't need to subtract 1 from it. Then over here we go positive 2 to the n minus 1 minus 1. So if we did our example where you said n is equal to 4, I'd have negative 8 now over here going up to positive 7. Notice that I was able to represent 8 negative codes, 7 positives, and then a 0. So I was able to get 16 unique codes. I've extended the range of it. Now it's not necessarily symmetric, but I couldn't represent a positive 8. Why couldn't I do that? Because I've used all my positive codes. If I went and added one more to this code, I'd go to 1, 0, 0, 0. Now you have a sign bit that's equal to 1, and that violates the whole theory of a signed number. So we have 3 sign number codes. We have sign magnitude, 1's complement, and 2's complement. Sign magnitude and 1's complement are not used anymore. 1's complement is an operation that we use within 2's complement, but every computer now uses, well, I shouldn't say every, but the majority of computers today use 2's complement due to the fact that we use all the unique codes and it preserves this rollover aspect.